So I'd like to welcome Saurabh Verma, the Vice President of Analytic Applications in Software Development for Oracle Analytics. You know, COVID has brought out about a new set of challenges for the entire world, and Saurabh and his Oracle team used Oracle ADW and Oracle Analytics Cloud to analyze and interpret self-reported symptom data. This is a new class of applications which came about to track COVID symptoms through self-reporting. So today's session talks mostly about participant behavior and symptom profiles while dealing with the event streams with sparsity. Go ahead and take it away, Saurabh.
Thanks, Dan, and a very welcome to this talk. Can you see my screen now?
Yes, I can. That's great. Looks great.
Yeah, okay. So today I'm going to talk about an interesting data analysis problem that we encountered for COVID-related product that Oracle has helped build for healthcare organizations throughout the world dealing with this emergency. When the pandemic hit in March, Oracle also volunteered its resources to help the government with our expertise, our resources, data centers, and the talent pool to help solve some of the critical problems that the health systems were facing. We'll talk about one of those interesting problems in detail today. So with that background, let me go over what we intend to cover today. We'll first explain what's the nature of data collected through these self-reporting applications. We'll cover what were the basic analytic needs that our consumers were really using the product for. What additional questions came up that were not possible to answer through simple analysis and aggregations and visualizations. Then we'll get into the need for clustering, which is really the focus of this talk. We'll look at some of the techniques used in the algorithms. And then we'll talk about some of the results and findings and the insights that we were able to get, which was not possible otherwise with the basic reporting that we had built initially. And lastly, we'll talk about the applicability of this technique in other domains in enterprise software. The technique is very generic and can be applied in several areas. It's a little surprising that we don't use it more often in the enterprise world as of now. Now, coming to this specific application, like Dan mentioned, with COVID, a new class of applications called surveillance applications came into being last year. As you can imagine, one of the key issues in early stages of COVID was symptom and behavior monitoring, especially when the testing was limited in the initial stages. That is, how do you know where the spread is happening? Who's affected, what kind of symptoms are showing up in the population, and how does it differ across regions, demographics, age groups, genders, etc. Especially like when the tests were not available very earlier on. So that was the genesis of these self-reporting applications. So the whole idea was if you sign up a bunch of people who are kind of reporting their symptoms on a nightly basis, you get an idea of where the spread is actually going on. So essentially, many such products have been built, and Oracle also contributed in building a product which lets participants self-report symptoms on a nightly basis. The participation is voluntary, and the product is in use by around 15 plus health systems in the East Coast and is expanding to several other countries recently. So before we get into the need for analytics, let's first look at what data is captured from the participants and what kind of issues happen in using that data. So essentially, the volunteers, which are typically the members of the health systems, once they sign up, they get a link every night. And they provide the following information on a nightly basis. So first of all, there's a set of symptoms which have been identified by CDC as possibly related to COVID. So they basically check if any of the symptoms were experienced during the day. And they also provide a few answers on other health parameters, any treatments, any hospitalizations, as well as exposure and contact with others having COVID. They also have answered a few questions on mask usage. Um, and lastly, the survey occasionally captures information about additional topical events like Thanksgiving holiday, winter break, how many people did you meet during these events, um, and whether you intend to take a vaccine or not, and also capture if the participant has taken a new COVID test. In parallel, the health systems have an arrangement with the test providers, and they get a feed of the test results from the providers directly as well and load into the Oracle Cloud. So all of this data is directly captured in the Oracle Cloud on a nightly basis. The process takes around 20 to 30 seconds to complete. And surprisingly, there's a healthy 75 to 80% response rate on the survey. So we are quite surprised with how frequently people are reporting. So before we get into analytics, let's quickly take a look at the architecture. So in terms of the overall architecture, the system is hosted on Oracle Gen 2 cloud infrastructure using Oracle Autonomous Data Warehouse and Oracle Analytics Cloud. The data from the transactional app is extracted into Oracle Object Store and then loaded into Autonomous Data Warehouse. Additional tables and materialized views are created to reshape the data into a dimensional format. The data warehouse is multi-tenant, and we use VPD policies and a second layer of secured views to control visibility to each of the health systems. Each health system has its own analytics instance though, so that is not multi-tenant, and they can view their and store their own reports, visualizations, and content and share it with other users. So in terms of architecture, it's a very standard analytics architecture and nothing out of ordinary in it. Now, in terms of consumers of the product it's used by two sets of teams, the retention and the recruitment team, who basically are responsible for signing up of participants, tracking participation, monitoring opt-outs and attrition, and incentivizing the participants to provide regular updates. They run the campaigns to sign up different population segments and make sure they're actively engaged. The second group are the principal investigators and the hospital administrators. So they are the ones who actually analyze the symptoms which are reported. They look at the medical tests and come up with various analysis like hotspot detection, test results, antibody prevalence, etc. The need for two of them were very different, and you had to work separately for the solutions for each of the teams. Most of the reporting was actually done by a set of analysts who were responding to questions from senior doctors and PIs and administrators. So the doctors and PIs are the ones who are coming with various hypotheses and the really difficult questions which these analysts had to actually build for. The project started with some very basic reports on daily symptoms and participation. We are doing basic aggregations like counts, sums, averages, etc. So nothing out of ordinary again, some basic formulas. And then we expanded to the second phase where more data and surveys were captured, which we basically built very simple analytics. With over time, as the usage increased and they signed up tens of thousands of participants and the data volume kind of grew quite a bit with millions of records flowing in, we started realizing that there are more complex requirements which they were coming up with, which are harder to answer with some of the analytics we had built. So, for example, clearly people don't report every day. How do you handle missing records? For example, if somebody has symptoms on day 1, 2, and 5 and missed the day 3 and 4 in between. So how do you say that same symptoms kind of persisted for multiple days and were probably present on the missing days as well? So there were a lot of analysis where they had to look at the rolling window and required interpolation for missing records for different combinations. They also started asking questions on other behavioral patterns and symptom evolution. And we started realizing that the basic reporting techniques are not answering some of the questions which they're coming up on both the participant usage and retention, as well as symptom tracking. And we possibly have to do something different here. Is the same problem which probably Netflix had in terms of having very fine-grained data for the user to movie rating, and how do you make sense out of it unless you have some higher level concepts introduced into the mix. So we were looking at various options on how to resolve it. And like I said, what was really limiting their ability to analyze the stream of data was sparsity. People are not reporting every day, and extremely fine grained data. As the volume increased, they were having hard time just making sense of what's going on by looking at essentially at participant level, or trying to understand behavior by looking at what happened with a small group of participants. So for example, the questions which are coming up were, how long was someone sick? When did it start and end? And again, there are no clear boundaries here. So how do you answer the question? How do we know that a group of symptoms was flu or COVID or just diarrhea, or somebody fell sick and had body ache for a few days? Then there were some CDC reporting requirements, like can you track symptoms for 14 days or longer when somebody is sick and summarize it? And that was a little tricky as well. And lastly, because there are two streams of data here, like I said, there's a stream of data which is the symptoms, which is coming from the participants, and the other stream, which is the medical tests, which are provided by the test providers. So the question was, how do you correlate the two and basically say that this particular set of symptoms was related to COVID versus not. Similarly, on the participant behavior, there were questions like what segment of people are reporting regularly versus not. Do people drop off and come back to reporting if they start experiencing symptoms again? So they had this hunch that people are dropping off and they're not interested somehow, but when they fall sick, they come back again. And they were not able to quantitatively and confirm and say, yes, that's indeed happening, and their retention team needs to do something. So that was another question they were having hard time with. Another hunch they had was that if there's a gap between the reports of a particular person, they're more likely to churn altogether. But again, given the stream of data, it was hard to quantify and say, is there a really some indicative factor there? So given these questions, we started looking at options to make sense of this data, and realized that grouping and clustering this fine-grained stream of events can help answer many of these questions. We looked at various options and ended up utilizing Oracle database features for pattern recognition and create groups within this stream of event data. And the solution turned out to be fairly compelling and useful for our users, and demonstrates the best of ADW and OSC working together. So now let's look at the example of a symptom stream for a single participant. So essentially, this is what a participant is kind of reporting. Each color here in the bar is a symptom that they experience for the day. And this example has more visual emphasis that I've put in. Many a times it's not clear when you look at the actual data, what's going on here. So this person reported a group of symptoms in March and then some intermittent symptoms, followed by another group with a different symptom profile later in the April timeframe. So the idea was that if we can specify clear boundaries here and group these symptoms using a set of initial and terminating conditions, then we can summarize what's happening between those days. You can look at the summary and say most likely this was COVID or flu or something else. The second aspect of this, like I said, there's a test stream which is coming in. Um, this person, for example, was tested in early March and then late April and late March and then again late April. The green bars are basically a negative COVID test and the red one is a positive COVID test. So once you have identified these clusters, it was easier to correlate a cluster boundary to a specific test and say that most likely this group of symptoms came from non-COVID illness versus this group of symptoms was related to a COVID illness. And once you have that, you can actually segregate all of these symptoms and just focus on the set of clusters which are actually correlated with positive COVID scenarios. So similarly, for participant behavior, we kind of extended the same idea. For example, here, each one represents a report on that day from a participant, and 0 is a missing report. It was again very hard to make sense out of this kind of data for tens of thousands of participants with millions of records. For the questions that they had, that do people come back when they have fallen sick, we again started clustering these into groups until there's a break of 5 days. Which was just an arbitrary gap that we picked. And once you have these clusters, you can do a lot of computations which are harder with that fine-grained stream of data. Basically, you can figure out that within this cluster, were there more symptoms reported per reported than the first one. You can also calculate what is the gap between each of the clusters. Are there indicators that somebody is likely to drop off by just looking at the gaps? Do different age groups, demographics behave differently? So a lot of these things we were able to start computing once we created the clusters. So now let's take a look at the secret sauce behind how this logic was built. We used Oracle's match recognize feature to do clustering in both the cases. It's a very powerful but little known feature in the Oracle SQL language. The way to think about it, it's basically a where clause for shapes. The regular where clause checks for individual rows, whereas the match recognize can detect a shape in the curve and return that subset of graph to you. So on the right is the famous example from Oracle documentation about finding the V shape in a stock price curve. Essentially, you define a set of conditions as up or down and arrange them in a specific pattern sequence for match recognize to look for that pattern and return that subset. So in this graph, for example, for the red stock, there are probably 1, 2, and 3 V-shape set of rows, and that's what match recognize would return. Full syntax for match recognize, essentially, there's a select clause on the top, which lists the columns that you need, followed by a partition clause, which defines the stream that you want evaluated in the order of rows. For example, here you are partitioning by stock symbol and ordering by timestamp. Measures is a set of columns that you want returned. You can do additional computations. You can do cross-row lookups. You can and return whatever desired columns and computations you need. The most important clauses are define and pattern, which is what I've highlighted. So essentially, you define a set of conditions. For example, down is price is less than the previous price and up is price is greater than previous price. And then arrange them in the pattern clause. So you start with a row and you're saying that I want at least one down and at least one up. So every time match recognize finds those conditions satisfied, it'll return that set of rows. The pattern uses regex syntax. So if you're familiar with that, you can control the exact matches with the regex expression, and any arbitrary condition can be modeled very easily. It's extremely powerful in its expressibility. Now, let's look at how this was applied to the stream of data for symptom reports. So this is a data stream for a single participant. Now, imagine there's a moving window with multiple conditions. So each of them is a condition that I showed earlier in the define. There's a set of initial conditions, ongoing symptoms for a few days, and terminating conditions. So we had a set of symptoms which are tracked for 5 days as initial conditions by looking at data incorporating various missing row conditions, various symptom combinations, etc. It was fairly complex logic. Then we tracked the ongoing symptoms for another 9 days and terminating conditions when the symptoms are wearing off. You can have any number of conditions in the pattern clause. The smaller boxes can be fixed with a variable. So in our case, the first two were fixed with. We are looking at only 5 and 9 days specifically, whereas the third condition was more variable, and it tracked till a patient continued reporting symptoms. And again, to repeat, the entire power of regex is at your disposal here. So in terms of exact conditions, a small code snippet was much more complex than this. So this is what we coded. Essentially, the initial symptoms was a set of symptoms looking across different day boundaries, taking into account some of the sparsity conditions and all. So it was a pretty intense like initial set of conditions. Then followed by the Windows 14-day clause, which just looked at symptoms for another 14 days. And lastly, we continued tracking the symptoms for more than 14 days. And they were arranged again in the pattern clauses. The moment you find initial symptoms, window for 14 days, and anything beyond 14 days, which is marked by star here, then regex would return those set of rows. So now that we have a cluster identified for a specific participant, imagine you can do that across tens of thousands of participants and millions of symptom records. So each of the horizontal lines here is a participant's data stream, and the boxes are the detected clusters. So see the beauty of it. Now you can aggregate a query across all of these participants across all the clusters. We can see what's happening with symptoms on day 1 to 5 across all the windows, or day 10 to 15, or the entire cluster boundary. You want to see how the symptoms change over time. You can do that. So you have a cluster number and a running day number within each cluster, enabling a lot of this analysis. You can also slice and dice this by different ethnicities, different geographies. Like for example, if a particular variant of the virus is causing problems in certain geos, and you just want to like focus on that and see what symptoms are showing up there on what day, you can just filter by that geography and aggregate only those clusters. So now, once that was done, coming to some of the results, So this is exactly an aggregation of symptoms over these clusters that I just showed. Um, so one of the questions that was being examined was how do these symptoms change over time? So in these bars, each color is a symptom reported by a participant. And you can see that how over the first 28 days of sickness, first of all, how does the overall symptom profile change? How long does it even last, even beyond 28 days? And within each day, you can see what's happening in the earlier part of sickness. Maybe loss of taste and smell is something which is showing up more than in the later part. So all this was possible once you had these clusters and you could kind of aggregate across them. Um, uh, this graph is basically um, a aggregate over all the clusters, whether they were ultimately correlated as a positive or a negative bout of sickness. But another analysis that we were able to do, which shows how the symptoms differ between the positive and the negatively correlated clusters. So on the right is an aggregation of negative clusters, and the left are the positive clusters only. What I'm showing is essentially the symptom profile for first 5 days of sickness. So you can see that the symptom profile is vastly different. There's some symptoms which are significantly different in terms of occurrence between the two groups. This is obvious even without any statistical significance test. You can also slice and dice this by like the entire duration or specific ethnic groups or gender or geography. If you feel the uh, certain strain may be more prevalent in certain groups or geographies or locations, etc. So a lot of this analysis was possible once these symptoms were kind of clusters and specific episodes or bouts of sicknesses identified. Coming to another interesting analysis, they had this question that are people usually dropping off and they come back when they're sick? This is a plot of clusters on the X. So each cluster is basically a group of reports that they had, a participant had submitted till there was a gap of 5 days, as I mentioned earlier. And we computed what's called a symptom density per cluster, which is basically out of the number of reports that he had, what was the average number of symptoms reported. So you can see that as you move to the right, the later clusters have higher symptom density than the earlier ones, confirming the initial hypothesis. That's indeed the case, that people drop off. And once they fall sick, they log into the system and start reporting symptoms again. It's not going to make them feel better, but it's probably just something psychological going on there. Another question which they had was related to gaps. And you can see that the gaps are fairly high between the second and the 10th cluster, and then they drop off. This is a little surprising, as the expectation was that as the gaps increase, the um, as the gaps increase, as they go to the right, probably there are more irregular people there, and probably the average gap between clusters should increase. But the actual data showed us something else. And the explanation was that probably once that becomes a habit, people keep reporting. So people on the right are actually more regular ones. It's just that they drop off once in a while, and it's kind of become a habit. Whereas the more risky people are in the initial stages. So it's the second to 10th cluster or the first 50 days, which are more important for overall retention. So these are some of the insights we are able to get. They are doing a lot more with this. This is just a few illustrative examples. Now moving on in terms of performance characteristics of match recognize. One of our worries was that the performance may not be that great. However, even with a 1.5 to 2 million raw data set, we were getting 2 to 3 second response time, which was excellent. However, we did have some very dense dashboards where this function was being called multiple times, resulting in 7 to 8 seconds rendering. So ultimately, we did materialize the results in a batch process to optimize those dense dashboards, because our goal was dashboards should come back in 2 to 3 seconds. Otherwise, people lose interest. So only for that reason, we kind of materialized. But for a single analysis, I wouldn't hesitate to use match recognize in a live query. The performance is very good compared to what we had expected. Also, these clusters and some of the analysis we have done is leading to additional questions being asked. One of the questions is that, can you score a participant in terms of COVID risk? As we saw that the symptom profile for a first 3 to 5 days of a participant is very different for positive versus negative COVID cases. The question we are looking at, can we score their COVID risk by just looking at their first few days of symptoms, and we're trying to use some machine learning classification to enable that on top of these clusters. Another question is the length of antibody persistence. So one of the big questions that's still open is how long did these antibodies last? And as we're getting more and more data, again, it's a clustering problem, because you get this whole chain of events like positive, negative, with a lot of false positives and negatives. And you just have to figure out specific logic of when somebody turns negative from positive. So we are looking at that as another application of a similar technique. Now, having covered this, match recognize doesn't need to be limited to stream data or COVID or such scenarios. It can be applied to many standard business scenarios. Whenever you want to search for a shape of a curve, you can use this technique. So few examples, like employees whose performance went up or was constant, or they went down following a manager change. You want to search for it. It's again a shape detection problem. You can use match recognize for it. Few more examples in more detail. This is the famous opportunity chart. So again, it's a shape, kind of a situation that there's a particular shape which you will call a healthy pipeline. You can do this analysis in aggregate, but if you want to search through various products, geos, sales teams, business units, etc., and see where the shape of the curve is outside the acceptable norms, you can search at that fine grain level of data using match recognize. Another example, your account receivable aging bucket performance. Again, there's possibly a specific shape which is healthy for the business, and you want to search through different customer segments, business groups, etc., to see where the shape of the curve is deviating. That should be possible. Another example, inventory balance. So possibly there are two anomalies here. The balance fell very fast here. Or alternatively, there's an opportunity here that why was nothing happening here. So it's not really something wrong, but a constant level of inventory can also be an opportunity for a business improvement. So wherever you want to search for a shape of a curve with certain tolerances, you can kind of model that here. So in summary, this technique can be applied to several business scenarios in enterprise software, other areas with rapid results. This would be another tool in the arsenal which lies between basic aggregate reporting on the one side of a spectrum and machine learning on the other side of spectrum, which requires a lot more effort to succeed. Whereas something like this, or pattern recognition, is extremely easy to do and can produce results in days or hours. It can deliver a lot of business value with, I would say, little to medium effort. I hope this was a useful overview. And with that, let me open this up for any questions that you might have.
Thank you, Saurabh. In the interest of some time, I think we're going to ask if you would be willing to take some questions that people put in the Q&A box and handle them offline so we can get on with the rest of our presentations this morning. You okay with that?
Oh, absolutely, Dan. Yeah, thank you. So in that case, let me hand it back to you.
Thanks. And I think you're definitely, that was actually fascinating. I think we're going to have the recording of this and people will want to look at that. Definitely worthy of the image of you replacing Mr. Spock on that.
Live long and prosper for sure.
Yeah, definitely. I like that.